Hello everyone. This is a brief presentation on CCMR, a high-resolution optical flow estimation approach. Let me start this presentation by defining the problem. What is optical flow? Given two consecutive images from an image sequence, we want a displacement field between the two images. For example, how the pixels from this image moved in the other image. You can see the optical flow here that is shown with small arrows, and here you can see a color coding. Now, let us motivate our approach. 3 years ago, an approach called draft became very popular. It was the new state of the art, and the network was quite compact and accurate. These two methods that I listed here are based on raft. MS-Raft or MS-Raft Plus, both were multi-scale variants of raft, and they yielded highly detailed flow fields, and they were excellent in non-occluded regions. On the other hand, GMA was a single-scale approach, and they computed the flow on 1/8 the resolution like in raft, and their flow fields are not as detailed, but they introduced a very nice motion aggregation concept. Their idea was motion of partially occluded objects could be inferred by its non-occluded parts, and they implemented it using a token attention. Now, here they gained very, very good results in occluded regions, unlike in MS-Raft, MS-Raft Plus. Now, can we combine the advantages of these two worlds? Our solution is CCMR. We combine multi-scale estimation and motion aggregation concepts. So our method yields highly detailed flow fields. It is excellent in non-occluded regions, and we have a multi-scale motion aggregation concept. But we do so via channel attention, and we use a low amount of VRAM comparably. And we also gain excellent results in occluded regions. So we get what we wanted, excellent results in occluded and in non-occluded regions. Let us now talk about the architecture. On the right-hand side, you can see the architecture of CCMR, which is obviously a coarse-to-fine approach. First, the flow is computed on 1/16 the resolution. We get some flow, we upsample it, we get a flow at 1/8 the resolution. We use this flow as initialization in the next finer scale. And then the procedure is repeated until we get the flow at 1/2 the resolution, and then we upsample it to the original resolution. Please note these 3 dots. For compactness, we didn't show the 3rd scale. Now, you should note that we have a lot of inputs here. F1 and F2 are image features from which we compute matching costs. I will explain that. And C is the context, GC is the global context, H is the hidden state of the crew, which is inside this matching module. And the matching module has a few operations in it, including cost sampling, motion encoding, and refinement. Introducing a multi-scale motion aggregation concept in our approach is not our only contribution in CCMR. We also improved the feature and context encoder. You can see its architecture on the right-hand side, where we added an activation-free conv after the residual unit to aggregate the multi-scale features. For more detail on why we do this, please check out the paper. Since I really don't have a lot of time to talk about the approach in this presentation, I kindly refer you to this paper. We showed 2 slides before that CCMR computes the flow in a coarse-to-fine manner. Now, we had a lot of inputs for each block at each scale, right? Now, we want to show how we computed image features, context, hidden state, and a global context. Image features are actually just the output of our feature encoder that you just saw 1 slide before. The context and hidden state are computed similarly. We pass only the first image through our encoder that you saw in a previous slide, and then we split them We stack them, we aggregate them, and then we split them. Half of the features are activated with ton H and the other half with ReLU. Hs is the hidden state, or you could also say the initial hidden state of that specific scale S. And the other one, the other split, is activated via ReLU, and we call it context. And context is always computed only from the first image, unlike the image features. Now, how do we compute the global context? We want to have a more global self-attentive context features. Now, for this, for each scale in all our coarse-to-fine scales, we pass this context on scale S, on each scale, through a self-attention excite unit. So we compute features, key query values, and then we pass them through a cross-covariance attention module, and after that a local patch interaction and a feed-forward network. Like this, we get our global context. Please note that unlike the approach of excite, the original approach, we do not explicitly patchify the input of our excite module. We directly process the context that we get at each scale, also for the fine and high resolution scales. Now, let us talk about how we compute the flow in each scale. So here we are talking about the matching module that we showed in the coarse-to-fine architecture. You can see here the features, scale-specific features of both images, F1 and F2. We sample the costs based on some current or initial flow. These costs and the current flow are then encoded via motion encoder module. We get the motion features and use it as one of the inputs of our update block. This update block has a cell in it, and it iteratively updates the flow. Another input of this update block is actually the context that we just talked about in the previous slide. Now, how do we want to aggregate the motion per scale? And this is also the architecture per scale. You can see that these tensors have S in there as a subscript, so it is per scale. We aggregate motion features and the global context that we just got from the previous slide. And from the global context, we compute features, keys and queries, and the values we compute from the motion features. We pass them through a cross-covariance, cross-attention module, and then again an LPI and FFN layer. And this is the outcome of this is another input to our update module. So we use the global context as a base to aggregate motion features. Channel attention is not as adaptive as token attention, right? Yeah. But our results show that using channel attention in our case was still very effective, and it is much more feasible. In fact, we extended GMA to multiple scales using its token attention, and it needed an enormous amount of VRAM. For example, for inference, a synthesized image needed 80 gigabytes of RAM, while our CCMR approach only needed 5 gigabytes of VRAM. For training, this is even more problematic. Using GMA or our schedule, training the extension of GMA needs more than 1 terabyte of VRAM, while our approach needs 94 gigabytes for training. CCMR achieved state-of-the-art results on both Scintille and Kitty benchmarks. It was rank 1 on Kitty and rank 2 on Scintille, and it yielded highly accurate results in both occluded and non-occluded regions. If you zoom in the paper in these flow fields, you can see how detailed our results are compared to other state-of-the-art methods. That was it. Thank you for your attention. The code will be available soon. Please check out the paper. And if you're interested in my research, don't hesitate to contact me.